On April 6, 1917, President Woodrow Wilson stood before Congress in Washington, D.C., his voice steady but carrying the weight of history as he declared that the world must be made safe for democracy. America declared war on Germany that day, and within hours, procurement officers at the War Department began tallying everything America would need to fight this unprecedented conflict. They counted ships, rifles, artillery, and aircraft, compiling endless lists of military necessities. Then someone in that room asked what seemed like a simple question about where they would get spark plugs for all these engines, and the room went silent because the answer was absolutely devastating. Every spark plug in America, every single one without exception, came from one source: Robert Bosch GmbH in Stuttgart, Germany, which meant they came from the enemy. The numbers facing America were brutal in their simplicity and terrifying in their implications. America's Army Air Service possessed exactly 55 operational aircraft, while Germany fielded over 2,500 warplanes. Britain had 1,782, and France had 1,328. The numerical gap was staggering, but it wasn't actually the real problem that would determine whether American forces could take to the skies. The real problem was hidden inside every engine in the form of high-performance spark plugs that could survive the extreme conditions of aircraft engines with their compression ratios of 6:1. Combustion temperatures exceeding 1,800 degrees Fahrenheit, and mechanical vibrations that would rattle apart anything even remotely fragile. Robert Bosch had dominated global spark plug production since 1902, when engineer Gottlob Honnold invented the first commercially viable high-voltage spark plug with a design featuring porcelain, insulators, precision-machined electrodes, and perfectly calibrated gaps that had become the worldwide standard. The patents were German, the manufacturing expertise was German, and the supply chain was German. And as of April 6, 1917, it was all completely cut off from American access. American automobile manufacturers had been content to import Bosch plugs for years because there seemed no reason to invest in developing domestic production when German plugs were demonstrably superior and readily available through established commercial channels. Now that complacency had transformed into a national security crisis of the first order. The War Department conducted an emergency assessment and discovered that current American spark plug production capacity suitable for aircraft engines was zero, not limited or insufficient, but absolutely zero. Albert Champion was born in Paris in 1878, and his first career had nothing whatsoever to do with engines because he was a bicycle racer, and a remarkably good one at that. By his early 20s, Champion had become exactly what his name suggested when he won races across France, including the prestigious Paris-Roubaix in 1899, drawing crowds of cheering spectators, attracting sponsors willing to pay handsomely, and achieving the kind of fame that young athletes dream about. Then came motor-paced racing, a thrilling and dangerous sport where cyclists would race behind motorcycles, drafting in the aerodynamic slipstream and reaching speeds over 60 miles per hour. And Champion excelled at it until August 1903 at Brighton Beach in Brooklyn, New York. His motorcycle pacer crashed at high speed, and Champion, unable to avoid the wreck, slammed into the pile of twisted metal, suffering a compound fracture of the femur that left him, after the doctors finished their work, with one leg 2 inches shorter than the other and his racing career over at age 25. During his recovery in France, Champion noticed something about the motorcycles that had paced him throughout his career, the engines that had powered his success and then ended it, noticing that they all had terrible spark plugs that failed constantly, overheated, misfired, and required replacement after every few races. If he couldn't race anymore, perhaps he could fix the machines that had defined his life. In 1905, Champion returned to America with backing from two businessmen, Frank and Robert Stranahan, establishing the Albert Champion Company in Boston to import French electrical components. By 1907, Champion was manufacturing something genuinely revolutionary: the first American-made spark plugs using ceramic insulators that would change everything about how engines could perform. Before Champion entered the field, American spark plug manufacturers used two materials for insulation, either mica or crude porcelain, and both had fatal flaws that made them unsuitable for high-performance applications. Mica absorbed moisture. Wet mica conducted electricity, and the result was misfires and engine failure at the worst possible moments. Crude porcelain cracked under thermal shock because engines cycled between rich and lean combustion with temperature swings from 400 degrees Fahrenheit to 1200 degrees in just seconds, and porcelain simply shattered under those conditions. Champion imported a special clay from France and developed a kiln firing process that created ceramic insulators superior to anything American competitors could produce, with three critical properties that made all the difference. The material had heat resistance that could withstand sustained temperatures up to 1200 degrees Fahrenheit without degradation, thermal shock resistance that survived rapid heating and cooling cycles that shattered ordinary porcelain, and electrical insulation properties that prevented current from leaking from the center electrode to the metal shell, even when contaminated by combustion deposits. The manufacturing process was extraordinarily complex, requiring workers to grind French clay to fine powder, mix it with water and binding agents, extrude it through steel dies to form the insulator shape, bisque fire it at 1800 degrees, apply glaze, conduct a final firing at 2372 degrees, and then grind everything to precise dimensions. Each step required expertise that took years to develop, and Champion had that expertise while his competitors didn't. By 1908, his spark plugs were gaining serious attention from industry leaders, and William C. Durant, founder of General Motors, approached Champion with a proposition to relocate to Flint, Michigan, and manufacture spark plugs exclusively for Buick. Champion agreed to the arrangement, but there was a significant problem because Champion didn't actually own the company that bore his name, since the Stranahan brothers controlled it financially. Personality conflicts emerged between Champion and his financial backers, with Champion wanting innovation and continuous improvement, while the Stranahans wanted predictable production and steady profits. By 1909, the relationship collapsed completely, and Champion quit the company with his name on it. Unable to use Champion due to contractual restrictions, he founded a new company called AC, Spark Plug Company, using his initials Albert Champion, since the legal settlement prevented him from using his own surname commercially. Two competing companies now existed, both based on Champion's innovations and both claiming his legacy, but AC Spark Plug quickly proved superior as Champion continued refining his ceramic formulation, developing better electrode designs, and improving manufacturing processes. When America entered World War I in 1917, both companies existed, but neither was producing at industrial scale, and that was about to change dramatically. On May 29, 1917, at the Willard Hotel in Washington, D.C., two engineers checked in with an impossible assignment. Jesse G. Vincent from Packard Motor Company and Elbert J. Hall from Hall Scott Motor Company had been given the task by the Aircraft Production Board to design a new aircraft engine from scratch that could be mass-produced by multiple manufacturers, and their deadline was just 1 week. For 5 days, Vincent and Hall worked around the clock, combining proven features from Packard, Hall Scott, and captured German Mercedes engines, and on June 4th, they emerged with complete drawings for the Liberty L-12, a water-cooled V-12 engine producing 400 horsepower. By July, Packard had built a working prototype, and by August, the engine passed all required tests with flying colors. In fall 1917, the War Department ordered 22,500 Liberty engines with contracts divided among Ford, Lincoln, Packard, Marmon, Buick, and Cadillac in an unprecedented mobilization of American industrial capacity. The Liberty engine was brilliant in its design, powerful in its output, reliable in its operation, and adaptable to mass production in ways that would revolutionize manufacturing. Ford revolutionized cylinder manufacturing, cutting costs from $24 to $8.25 per cylinder while simultaneously increasing production from 151 per day to over 2,000. But every Liberty L-12 required 24 spark plugs, and the engine simply wouldn't run without them, creating a mathematical problem that was brutal in its simplicity. 22,500 engines ordered multiplied by 24 plugs. Each meant 540,000 plugs at minimum, plus spares at a minimum of 4 sets per aircraft added another 540,000 plugs, plus maintenance replacements, since plugs wore out under operational conditions meant continuous ongoing production. America needed to produce over 1 million spark plugs within 18 months, but current production capacity remained at 0 plugs suitable for aircraft engines. The War Department faced 3 choices, and all of them were terrible. The first option was to import spark plugs from Britain or France, but Allied manufacturers were already struggling to meet their own desperate needs. Britain couldn't spare production capacity for American engines, and France was barely holding production together under wartime pressures. The second option was to license Bosch technology, but Bosch was German. Enemy patents couldn't be licensed during wartime, and even if they could, the Trading with the Enemy Act made it explicitly illegal. The third option was to develop domestic production from scratch, but no American company had demonstrated the ability to manufacture aircraft-grade spark plugs, and testing and qualification would normally take years. Except one company claimed they could do it. AC Spark Plug Company in Flint, Michigan, Albert Champion's company. Aircraft engines presented challenges that automotive engines didn't face in normal operation. Temperature cycling occurred as aircraft engines ran at full power for extended periods and then cooled rapidly during descent, and this thermal cycling shattered conventional porcelain. Combustion pressure from the Liberty engine's 6-to-1 compression ratio created pressures that cracked inferior insulators. Altitude performance became critical. Because at high altitude, reduced air pressure changed combustion characteristics, meaning plugs that worked perfectly at sea level failed catastrophically at 18,000 feet. Vibration from aircraft engines was intense and constant, requiring insulators to resist mechanical stress while maintaining electrical properties under conditions that would destroy ordinary materials. Champion's ceramic, an aluminosilicate formulation he had refined over years, solved all these problems, but the War Department required definitive proof before committing to large-scale procurement. Major Thurman Bain, chief of the engine section at McCook Field in Dayton, Ohio, designed a test protocol that was deliberately brutal in order to simulate the worst conditions that combat aircraft would face. The test involved running a Liberty 512 engine at full power, 2,000 RPM producing 400 horsepower, for a 50-hour continuous run while leaning and richening the mixture every 5 minutes to simulate combat maneuvers, conducting altitude chamber testing up to 18,000 feet equivalent, and then performing post-test inspection where plugs had to remain within specifications. The War Department tested 3 types of spark plugs under these identical conditions. German Bosch plugs from captured stocks averaged failure at 23.4 hours due to porcelain cracking from thermal cycling. AC Type C representing early American attempts average failure at 8.1 hours due to electrode erosion and insulator breakdown. But Champion ceramic core plugs achieved remarkable results with 18 of 24 plugs completing the full 50-hour test within specifications. The results weren't even close to competitive. Champion's ceramic cores operated successfully under conditions that destroyed everything else that engineers could throw at them. The material's lower thermal expansion coefficient, which was closely matched to steel, eliminated the stress fractures that killed Bosch's porcelain under thermal cycling. On October 12, 1917, the War Department issued contract number 43,891 for a quantity of 2 million spark plugs to be delivered between March 1918 and December 1918 at a price of 47 cents per plug, compared to Bosch's pre-war price of $1.20. Champion now had 6 months to scale from workshop production of 200 plugs per day to industrial output of 8,000 plus plugs per day. And the challenge seemed absolutely impossible. The Toledo facility, in October 1917, was a workshop rather than a factory, featuring handmade production by skilled craftsmen without any assembly lines or mass production capabilities. Champion needed to transform it into America's first mass production spark plug facility, and accomplish this before the 1918 spring offensive, when American aircraft would enter combat in significant numbers. He hired 847 workers in 3 months, and 67% were women, since most had no prior manufacturing experience because the male workforce had been largely conscripted, leaving women to fill the gaps and learn precision manufacturing on the job. The ceramic production line required 12 tunnel kilns imported from Ohio pottery suppliers, and these massive structures operated continuously at 2372 degrees Fahrenheit while consuming enormous quantities of coal and requiring constant monitoring by trained personnel. Raw materials became the first crisis that threatened to derail the entire operation. Bauxite, which provided aluminum oxide, had to be imported from British Guiana, but German U-boats patrolled shipping lanes, so Champion arranged direct Navy escorts for bauxite shipments, since spark plugs were classified as critical war materials, justifying military protection of supply ships. Copper was rationed for ammunition production, But Champion secured War Production Board exemptions by arguing that copper in spark plug electrodes was as essential as copper in shell casings for winning the war. Steel was rationed for shipbuilding, but again, exemptions were granted based on critical need and the recognition that without spark plugs, aircraft couldn't fly, regardless of how many airframes were produced. The assembly line evolved through continuous trial and error as workers and engineers learned what actually worked under production conditions. Initial production took 3.5 minutes per plug, but by March 1918, the process had been refined to 47 seconds per complete assembly. Quality control was government mandated at 100% inspection, meaning every single plug had to be tested before shipping to military depots. Rejection rates started at 23% in February 1918, which was unacceptable but expected during startup as workers learned their tasks. But by September, the rate had dropped to 3.1%, successfully meeting military standards for acceptable defect rates. The workforce faced brutal conditions that tested their endurance and dedication day after day. The kilns generated overwhelming heat throughout the facility, with summer temperatures in the plant exceeding 110 degrees Fahrenheit, while winter brought coal shortages as military needs consumed rail capacity, forcing workers to burn whatever fuel could be found to keep kilns operational and production running. Anna Kowalski, a 19-year-old Polish immigrant, worked the grinding station, and in a 1972 oral history, she recalled that she couldn't speak English well when they put her on the grinding station where workers had to hold ceramic rods against grinding wheels until they measured exactly right, using precise gauges where you couldn't be off even a little bit. Her hands shook for the first week from the pressure and responsibility. But then Mr. Champion himself came to her station, picked up one of her pieces, measured it carefully, nodded with satisfaction, and told her that this would keep a pilot alive. And after that moment, her hands never shook again because she understood the importance of her work. The production numbers tell the story of an industrial miracle accomplished under wartime pressure. January 1918 saw 47,000 plugs produced. March 1918 reached 183,000 plugs. June 1918 hit 524,000 plugs. September 1918 achieved 891,000 plugs, and November 1918, at peak production, manufactured 1,247,000 plugs. Total 1918 production reached 4,823,000 spark plugs, a scale that was unprecedented in the industry and pioneered techniques that would later be adopted industry-wide. These techniques included standardized tooling, interchangeable parts, rigorous batch testing, and continuous flow production, all implemented at a speed rarely seen outside the automotive sector. Behind these numbers was an intense collaboration between government agencies and private industry. Engineers redesigned factory layouts in real time. Raw materials were prioritized through wartime allocation boards, and training programs rapidly converted unskilled labor into competent production workers. Quality control was relentless, with random plugs pulled from lines and tested under simulated altitude and temperature extremes to ensure reliability. Failure rates dropped even as output soared, a combination many believed impossible at the time. By November 1918, over 20,000 Liberty engines had been built, with Ford alone manufacturing 415,377 cylinders before the armistice. Packard produced 6,500 complete engines, and Lincoln Motor Company, founded specifically to build Liberty engines after Cadillac founder Henry Leland quit GM in protest of pacifist policies, manufactured another 6,500 engines. Every single engine received Champion spark plugs, and the plugs performed beyond even the most optimistic expectations. Field reports consistently cited smooth ignition, reduced maintenance, and exceptional endurance, confirming that mass production had not come at the expense of performance. The true test came in France, where American pilots flew into combat. Captain Eddie Rickenbacker, America's top ace with 26 victories, flew a French Spad S-13 during most of his combat career, but American squadrons were transitioning to DH-4s powered by Liberty engines by mid-1918. On June 18, 1918, Rickenbacker engaged 6 German Albatros fighters over Chateau Thierry in his Espadille during a 14-minute dogfight that cycled from 18,000 feet down to treetop level with his Hispano-Suiza engine at maximum RPM throughout, creating rapid altitude changes, violent maneuvers, and mixture control cycling wildly. His combat report, documented as Combat Report Number 47 from the 94th Aero Squadron, noted that engine performance was faultless throughout the engagement, with no misfiring observed despite violent maneuvering and rapid altitude changes, and post-flight inspection revealed all 24 spark plugs remained within operational specifications. The 94th Aero Squadron maintenance logs documented the transformative impact of Champion's technology on operational readiness. In March 1918, before Champion plugs became standard equipment, aircraft averaged 4.2 spark plug changes per month with 7 engine failures attributed to plug problems. But by July 1918, after Champion plugs were installed, average plug changes dropped to 0.8 per month with 0 engine failures from plugs. American aircraft achieved a 73% operational readiness rate, far exceeding the Allied average of 52%, while engine-related mission aborts dropped from 14% in early 1918 to just 3.1% by summer. Most remarkably, 0 American combat losses were attributed to spark plug failure during World War I, a safety record that saved countless lives. German aviation intelligence treated the discovery as more than a minor technical curiosity. To inspectors already grappling with mounting engine failures at the front, the captured American spark plugs represented a quiet but devastating advantage embedded deep inside Allied aircraft. The October 1918 Flugzeugmeisterei report emphasized that these components directly affected operational readiness, noting fewer misfires at high altitude, improved cold starting, and far greater consistency during extended combat flights. German test benches reportedly showed Bosch plugs degrading rapidly under sustained thermal stress, while the American plugs maintained stable ignition even after repeated heating and cooling cycles. What alarmed investigators most was how mundane yet decisive the innovation appeared. Champion's single-piece ceramic insulator eliminated microscopic cracks that plagued multi-part porcelain designs, preventing carbon tracking and electrical leakage. The alumina composition, unfamiliar to German manufacturers, allowed tighter tolerances and higher firing temperatures without fracture. This was not merely a better spark plug, but a reflection of an industrial ecosystem optimized for mass precision manufacturing. The report's concluding frustration went beyond engineering envy. It implicitly acknowledged that Germany's wartime industrial collapse made technological parity impossible. Supply chains were fractured. Experimental ceramics required furnaces and raw materials no longer available, and the skilled craftsmen capable of such work were either dead, wounded, or still fighting. In that sense, the spark plug became a symbol of defeat, proof that even when Germany identified superior enemy technology, it no longer possessed the means or time to respond. Albert Champion didn't live to see his invention's full legacy unfold across the 20th century. On vacation in Paris, with his wife in October 1927, Champion collapsed during dinner at a hotel and died almost instantly of a pulmonary embolism at age 49. 5 months earlier, Charles Lindbergh had crossed the Atlantic using AC spark plugs and praised them publicly, causing sales to soar. So Champion was wealthy, famous, and at the peak of his influence when death claimed him unexpectedly. The man who started as a bicycle courier in Paris became a champion cyclist, survived a career-ending crash, and reinvented himself as an inventor, had permanently changed transportation technology, and his death was front-page news in American automotive journals. Today, 2 major spark plug brands trace their lineage directly to Albert Champion's innovations. AC Delco, formerly AC Spark Plug, is now part of General Motors and descended from Champion's 1909 company, while Champion, now part of federal mogul Tenneco, descended from his original 1905 company, which continued after he left. Both companies still manufacture spark plugs using ceramic insulator technology fundamentally unchanged from Champion's 1907 innovation, proving the enduring value of his original breakthrough. When World War I ended, Champion spark plugs had proven themselves in the most demanding application possible, which was military aviation under combat conditions, and the civilian market followed quickly, with Ford Motor Company making Champion spark plugs standard equipment on the Model T in 1923, General Motors signing an exclusive supply contract with Champion through AC in 1925, and Champion brands holding 90% market share in American aviation by 1930. The 1920s brought continuous refinements, including resistor plugs to reduce radio interference, extended tip designs for improved cold starting, and multi-electrode configurations for enhanced reliability. These developments were not incremental tweaks, but responses to the rapidly changing demands of aviation itself. Aircraft were flying higher, operating in colder air, and relying increasingly on radio communication for navigation and combat coordination. Spark plugs, once considered simple consumables, became critical system components. American manufacturers, led by Champion, invested heavily in metallurgical research, ceramics engineering, and large-scale quality control, ensuring that every unit performed identically under extreme conditions. This focus on consistency proved just as important as raw innovation. By the 1930s, all U.S. military aircraft specified Champion plugs as mandatory equipment, establishing a standard that would last for decades. This decision reflected trust not only in product performance but in supply reliability. Champion could guarantee uniform specifications across enormous production runs, something few European firms could match during the interwar period. Extensive military testing showed reduced engine fouling, longer service intervals, and improved ignition stability during prolonged high-power operation. Advantages that translated directly into aircraft availability and pilot confidence. When World War II began in 1939, America entered with mature spark plug manufacturing capacity that Germany could not match. While German engineers still produced capable designs, they faced chronic shortages of ceramics, skilled labor, and undamaged factory space. Between 1942 and 1945, champion companies produced 186 million spark plugs, a figure that underscored the industrial imbalance between the two nations. Spark plugs were never a bottleneck in American aircraft production, even as engine output increased and aircraft complexity multiplied. Every bomber, fighter, trainer, and transport rolled off assembly lines with ignition systems already proven at scale. The irony was complete. Germany, which had created the commercial spark plug industry through Bosch in 1902, found itself outproduced and out-innovated by an American industry that had barely existed before 1917. The shift illustrated a broader wartime truth. Victory increasingly depended not on isolated technical brilliance, but on the ability to turn innovation into mass-produced, reliable hardware. In that quiet, unglamorous domain, the spark plug became an unlikely symbol of how industrial capacity, logistics, and long-term planning ultimately outweighed early technological leadership. Every spark plug in your car, lawnmower, generator, or small engine uses technology descended directly from Albert Champion's 1907 through 1917 innovations. The centered alumina ceramic insulator uses the same alumina silicate formulation Champion developed, refined over the decades, but fundamentally unchanged. The center electrode with copper core was pioneered by Champion for better heat dissipation. The self-cleaning temperature range, meaning the concept that insulators should run hot enough to burn off deposits, but not so hot they cause pre-ignition, was Champion's insight. Single-piece construction, eliminating joints that could fail, was accomplished as Champion's design did, versus Bosch's multi-piece approach. Modern spark plugs operate at temperatures up to 1200 degrees Fahrenheit and voltages up to 60,000 volts. They're made from materials Champion never imagined, like iridium electrodes and platinum tips and advanced ceramics. But the fundamental design remains his. Global production exceeds 1.5 billion spark plugs annually, and the market Champion created in a Toledo workshop now encompasses dozens of manufacturers across every continent. In April 1917, America faced an existential vulnerability through complete dependence on enemy technology for a critical component that would determine whether it could even participate in modern warfare. Spark plugs weren't glamorous like machine guns or dramatic like fighter aircraft, but without them, every engine was simply a useless hunk of metal incapable of producing power. The solution came not from government laboratories or university research programs, but from a French immigrant who had been forced to reinvent himself after a racing accident ended his first career and who possessed the technical knowledge and manufacturing expertise to solve an impossible problem. Albert Champion's ceramic core spark plugs solved an immediate wartime crisis, but they did something more profound by creating an American industry independent of foreign technology and establishing manufacturing techniques that would define 20th century mass production methods. When Germany entered World War I, It possessed the world's best spark plug technology. But when the war ended, America had better spark plugs produced in quantities Germany couldn't match. That pattern of technical innovation combined with industrial scale mass production would become America's signature advantage in World War II and throughout the 20th century. The humble spark plug, dismissed as a simple commodity by those who didn't understand its significance, helped win a world war and launch the aviation age. German pilots, their engines misfiring at critical moments while American engines ran flawlessly through the most demanding combat conditions, never knew they were being defeated by ceramic cores invented by a Frenchman working in Ohio. Every time you turn your ignition key and your engine starts instantly without hesitation, thank the French bicycle champion who couldn't use his own name on his company but changed transportation history anyway. America had no spark plugs in 1917, but within 18 months, it had the best spark plugs in the world. And that's what happens when crisis meets ingenuity, when an immigrant inventor meets American mass production, and when ceramic chemistry meets the urgent demands of total war.